Hello, everyone. Um, Scary again. Gonna go ahead and film part two of this. I'll try to get a little bit of a video library up so we can schedule releases just in case I miss a day or two in between. Um, so I just filmed the building for the web introduction, section one, Hello Rust, all of that. So we're gonna go into 2.1 entities and components here. Kind of looking at it. It's a fairly long article here. So I'm going to just do this one article, and for any of these that look like they're fairly long, that's probably going to be its own video. Um, some of these seem shorter than others, but most of these are fairly long. So, anywho, that's probably what I'll do. And my goal really is to release one video a day. So I literally just today filmed part one, so we're gonna do part two just to try to build that library up. Um, okay, so here it says this chapter will introduce the entire of an entity component system, which will form the backbone of the rest of this tutorial. Rust has a very good ECS called specs, and this tutorial will show you how to use it and try to demonstrate some of the early benefits of using it. About entities and components. If you worked on games before, you may well be used to an object-oriented design. This is very common, even in the original Python libtcod tutorial that inspired this one. There's nothing really wrong with object-oriented design, but game developers have moved away from it, mostly because it can become quite confusing when you start to expand your game beyond your original design ideas. You've probably seen a class hierarchy such as this simplified one. Base entity, monster, melee, yeah. And this is not just games, but it's very common to see a hierarchy like this in most object-oriented programs. You'd probably had something more complicated than that, but it works as an illustration. Base entities would contain code data required to appear on the map as an entity. Monster indicates that it's a bad guy. Melee mob would hold the logic for finding melee targets, closing in, and killing them. Likewise, Archer Mob um, would try and maintain the optimal range and use their ranged weapon to fire from safe distance. Problem with a taxonomy like this is that it can be restrictive, and before you know it, you're starting to write separate classes for more complicated combinations. For example, what if we come up with an orc that can do both melee and archery? It may become friendly if you've completed the Friends with Greenskins quest. You might well end up combining logic for all of them into one special case class. It works, and plenty of games have published doing just that. But what if there was an easier way? Entity component based designs tries to eliminate the hierarchy and instead implement a set of components that describe what you want. An entity is a thing, anything really. An orc or a wolf or a potion, an eternal eth- ethereal hard drive can formatting ghost, whatever you want. It's also really simple, little more than identification number. The magic comes from entities being able to have as many components as you want to add. Components are just data grouped by whatever properties you want to give an entity. For example, you could hold the same set of mobs with components for position, renderable, hostile, melee AI, ranged AI, and some sort of combat stats component to tell you about their weaponry, hit points, etc. An orc warrior would need a position so you know where they are, a renderable so you know how to draw them. It's hostile, so you mark it as such. Give it a melee AI and a set of game stats, and you have everything that you need to make. Let me mute this. And you have everything uh, you need to make it approach the player and try to hit them. An archer may and be the same thing, but replacing melee AI with ranged AI. A hybrid could keep all the components, but either have both AIs or an additional one if you want custom behavior. If your orc becomes friendly, you could remove the hostile component and add a friendly one. In other words, components are just like your inheritance tree, but instead of inheriting traits, you compose them by adding components until it does what you want. This is often called composition. The S in ECS stands for systems. A system is a piece of code that gathers data from the entity components list and does something with it. It's actually quite similar to an inheritance model, but in some ways it's backwards. For example, drawing in an object-oriented programming system is often for each base entity called an entity's draw command. In an ECS system, it would be get all the entities with a position and render a renderable component, and use that data to draw them. For small games, an ECS often feels like it's adding a bit of extra typing to your code. It is. You take the additional work up front to make life easier later. That's a lot to digest, so we'll look at a simple example of how an ECS can make our life a bit easier. It's important to know that ECS is just one way of handling composition. There are many others, and there really is no right answer. With a bit of searching, you can find a bunch of different ways of approaching ECS. There's plenty of object-oriented approaches. There's plenty of free function approaches. They all have merit and can work for you. I've gone with the entity component approach in this book, but there are many other ways to skin that cat. As you gain experience, you'll find one that's comfortable for you. My advice: if anyone tells you that a particular method is the right one, ignore them. Programming is the art of making something that works rather than a quest for purity. That I love that statement right there. It really is. All right, so including specs in the project. To start, we'll want to tell Cargo that we're going to use specs. Open your Cargo TOML file and change the dependency section to look like this. So I'm going to just grab that. We're going to paste that in, save that, and it's downloading crates down there. That's fine. It says this is pretty straightforward. We're telling Rust that we still want to use RLTK, and we're also asking for specs. The version number this current time of writing this book, you can check for new ones by typing cargo search specs. We're also adding specs to derive, which provides some helper code to reduce the amount of boilerplate typing you have to do. At the top of main RS, we'll add a few lines of code. Okay, so make that RS. Looks like there's already RLTK, game state. We need to do RGB, virtual key code. Okay. We need to use specs, prelude, all, use std, cmp, max, min. I don't think the order of these matters. I would have done min max, but use specs, derive, component. Easy enough. Use RLTK colon in shorthand. You can type RLTK console every time you want a console. This tells Rust that we'd like to just type something, just type console instead. Likewise, you can use specs prelude star line here, so we aren't continually typing specs prelude world when we just want world. Old Rust required a scary looking macro use call, but you don't need that anymore. You could just directly use the macro. That's cool. Nice. We need the derivations from specs derived component. So we add use specs derived component. Okay. Defining a position component. We're going to build a little demo that uses an ECS to put characters on the screen and move them around. A basic part of this is to define a position so that entities know where they are. We'll keep it simple. Positions are just an X and Y coordinate on the screen. So we define a struct. These are like structs in C, records in Pascal, etc. a group of data stored together. Okay, so I am going to just say, hey, I would like just to go ahead and put my structs kind of together. Struct position, and if it's anything like C, it's I32, which is a 32-bit integer, Y I32 trailing comma, I guess. Okay, cool. Very simple. A position component has an X and Y coordinate as a 32-bit integer. That's, yeah. Our position structure is what is known as a pod, short for plain old data. That is, it's just data. It doesn't have any logic of its own. This is a common theme with pure ECS entity component system components. They are just data with no associated logic. The logic will be implemented elsewhere. There are two reasons to use this model. It keeps all of your code that does something in systems, that is, code that runs across components and entity and performance. Very fast to keep all of the positions next to each other in memory with node redirects. At this point, you could use position S, but there's very little to help you store them or assign them to anyone. So we need to tell specs that this is a component. Specs provides a lot of options for this, but we want to keep it simple. For the long form, no specs derive help would look like this. Okay. Yeah, so we could do it like this if we want to. You probably have a lot of components by the time your game is done, so that's a lot of typing. Not only that, but is a lot of typing the same thing over and over with the potential of getting confusion, potential to get confusing. Fortunately, specs derived provides an easier way. You can replace the previous code with, okay, so there's a struct position. How this works, derive. Okay. What does this do? Hashtag derive X is a macro that says, from my basic data, please derive the boilerplate needed for X. In this case, X is a component. The macro generates the additional code for you, so you don't have to type it in for every component. It makes it nice and easy to use components. The macro use use specs derived component from macro use before that? No, it wasn't. Or they're making this derived macros or special type of macro that implements additional functionality for a structure on your behalf. Saves lots of typing. Let's make sure that this still runs. Good. I have some warnings. It's saying things aren't used, but yeah. Okay. Um, okay, so we just read that. Defining a renderable component. A second part of putting a character on the screen is what character should we draw, and what color. To handle this, we'll create a second component, renderable. Uh, it will contain a foreground, background, and glyph such as an @ to render. So we'll create a second component structure. Okay. So struct rebel glyph RLTK font character type RGB RGB. I don't think we need to be doing that right there. Just a type, right? Yeah, we'll just drop that there. And then we need to derive that component again. Actually, we'll manually type that. Okay. I actually want to see what component looks like. Okay. AST gen. Okay. Okay. RGB comes from RLTK and represents a color. That's why we have to use RLTK RGB statement. Otherwise, we'd be typing RLTK RGB every time there. Saving keystrokes once again. This is a plain old data structure, and we're using the derived macro to add the component storage information without having to type it all out. Worlds and generation. So we now have two component types, but that's not very useful without somewhere to put them. Specs requires that you register your components at startup. What do you register with a world? A world is an ECS provided by the Rust crate specs. Um, you can have more than one if you want, but we won't go there yet. We'll extend our state structure to have a place to store the world. So in the state, we're going to say ECS world. That's right. Yep. And where does world come from? Um, oh, it's probably prelude here, right? So if we go in there, yeah, it's one of the preludes, I think. Yep. And now in main, we create the world. We'll put an ECS into it. Okay. So we let mute GS state equal. Okay, so we're modifying this line. ECS world. Notice that world new is another constructor. It's a method inside world type, but without a reference to self. So it doesn't work on an existing world object. It can only make a new one. This is a pattern used everywhere in Rust, so it's a good idea to be familiar with it. The Rust book has a section on this. So it's constructor. It's basically saying, hey, give me a new world. Okay. The next thing to do is to tell the ECS about the components we have created. We'll do this right after we create the world. So here we have gs.ecs.register. No, want that. Okay. Position gs.ecs.register variable. Okay, what is it complaining about here? Cannot borrow immutable local variable gs.ecs. It's mutable. Okay, so it's something about borrowing here. Okay, what does this tell? Hopefully it goes over how to fix that down there. But what is this? What this does is tells our world to take a look at the new types we're giving it and do some internal magic to create storage systems for each of them. Specs has made this easy so long as it implements a component. You can put anything you would like in as a component. Now, we've got a world that knows how to store our position and renderable. But I have this ECS thing here that I'm borrowing. Oh, okay. Oh, okay. Okay, it is telling me. I just didn't know to. Okay, that's fine. Um, okay, creating entities. Now we got a world that knows how to store our position and renderable components. Having these components simply exist doesn't help us. Beyond providing an indication of structure, in order to use them, we need to be able to attach something in the game. In the ECS world, that is something is called an entity. Entities are quite simple. They are little more than an identification number telling the ECS that an entity exists. They can have any combination of components attached to them. In this case, we're going to make an entity that knows where it is on the screen and knows how it should be represented on the screen. We can create an entity with both a renderable and a position component like this. So I'm going to just for create entity dot with, whoops, position 40 y 25 renderable glyph RLTK 437 at FG RGB RLTK named a black. I did not put a closing. If we run that, what happens? Absolutely nothing. Okay. But it builds. That's good. Okay, so we wrote that code. What this does is it tells our world, ECS and GS, that our game state that we'd like a new entity. That entity should have a position. We pick the middle of the console, and we'd like it to be renderable with an @ symbol in yellow on black. That's very simple. We aren't even storing the entity. We could if we wanted to. We're just telling the world this there. Notice that we're using an interesting layout. Lots of functions that don't end with a semicolon to separate out the end of the statement, but instead lots of dots to call another function. This is called the builder pattern. It's very common in Rust. It's kind of common in a lot of languages, but combining functions in this fashion is called method chaining. A method is a function inside of a structure. It works because each function returns a copy of itself. So each function runs in turn, passing itself as the holder for the next method in the chain. So in this example, we start with a create entity call, which returns a new empty entity. On that entity, we call with, which attaches a component to it, and in turn, uh, and returns the partially built entity. So we can call with again to add a renderable component. Finally, the build takes the assembled entity and does the hard part, actually putting it together for all the disparate parts, putting together all the disparate parts into the right parts of the ECS for you. You could easily add a bunch more entities if you want. Let's do just that. So for I dot dot I in 0 10, and we're going to do yeah, down a little bit, just like what they're doing. Yeah, there we go. And then we're gonna say I times 7 and then y 20. We'll do red, just like what they're saying. And we could do a smiley face there. That's fine. Alright, this is the first time we've called a for loop in the tutorial. If you used other programming languages, the concept will be familiar. Run the loop with I and set the value from 0 through 9. Wait 9 you say, Rust ranges are exclusive. Okay. They don't include the very last number in the range. That's yeah, because you're looping 10 times. You start with 0. That's why. Um, if you actually want to go all the way to the end, or so 0 to 10, you would write the rather cryptic for I, uh, 0 dot dot equals 10. Okay. You'll notice that we're putting them at different positions every 7 characters 10 times, and we're changed the at to a smiley face um, to CP437 as a helper RLTK. Let you type slash paste Unicode and get the equivalent member of its old DOS CP437 character set. You could replace the CP437 smiley face with a 1 for the same thing, or you could find glyphs available here. Okay. Iterating entities, a generic render system. So we now have 11 entities with differing render characteristics. Oh, I thought we were just modifying. That's fine. With different render characteristics and positions. It would be a great idea to do something with our data and our tick function that we last time. Yeah, here it is. We replace the call to draw hello Rust with the following. Okay, where you say let positions position let renderables read storage for post render in reference to positions, reference to renderables dot join. Yeah. Arrays ctx dot set x posts dot y render dot fg render dot bg render dot glyph. Okay. I think that should work. Let's run it. Let's see what happens. Ooh. Oh, CTX. This work? Sure does. I like it. Okay. What does this do? Let position self ECS read storage. Positions ask ECS for read access to the container it is using to store position components. Likewise, we ask for read access to renderable storage. It only makes sense to draw a character if it has both of these. You need position to know where to draw, renderable to know what to draw. You can learn more about these stores in the specs book. The more important part is read storage. We're asking for read-only access to the structures used to store components of each type. Fortunately, specs has our back for position, render. Okay. This line says join positions and renderables like a database join. It only returns entities that have both. It then uses Rust destructuring to place each result, one result per entity that has both components. So for each iteration of the for loop, you get both components belonging to the same entity. That's enough to draw it. The join function returns an iterator. In C++, iterators provide a begin, next, and end function. You can move between elements and collections with them. Rust extends the same concept, only on steroids. Just about anything can be made into an iterator if you put your mind to it. Iterators work very well with for loops. You can provide any iterator as the target for X in iterator loops. The 0 dot dot 10 we discussed earlier is really a range and offers an iterator for Rust to navigate. The other interesting thing here is the parentheses. In Rust, when you wrap variables in brackets, you are making a tuple. These are just a collection of variables grouped together. But without needing to go and make a structure, just for this case, you can access them individually via numeric access. My tuple.0 to each child. Or you can destructure them, 1, 2 equals 1, 2. Sets the variables 1 to 1 and variable 2 to 2. That's what we're doing here. The join iterator is returning tuples containing position and renderable components, and as .0, .1. Since typing that is ugly and unclear, we destructure them into the name variables position and render. This can be confusing at first, so if you're struggling, I recommend Rust by Examples section on tuples. ctx.set positions, render, all that. We're rendering this for every entity that has both a position and a renderable component. The join method is passing us both, guaranteed to belong to the same entity. Any entities that have one or the other, but not both, simply won't be included in the data returned to us. CTX in this is the instance of RLTK passed to us when tick runs. So yeah, it's this right here. It offers a function called set that sets a single terminal character to the glyph colors of your choice. So we pass data from position POS to position component for that entity, and the colors glyph from the render and renderable component for that entity. With that in place, any entity that has both a position and a renderable will be rendered to the screen. You can add as many as you like, and they will render. Remove one component or the other, and they won't be rendered. For example, if an item is picked up, you might remove its position component and add another indicating that it's in your backpack, or more on that in later tutorials. Rendering the complete code. If you typed all that in correctly, your main RS now looks like this. Yep, so we got it's in different order, but that's fine. You have your tick function, yeah, just a little bit better formatted. Then we have going on here, and then we have the main loop, yes. Running it with cargo run will give you something like, there it is. An example system random movement. This example showed you how an ECS can get a desperate bag of entities to render. Go ahead and play around with entity creation. You can do a lot with this. Unfortunately, it's pretty boring. Nothing is moving. Let's rectify that a bit and make a shooting gallery type look. First, we'll create a new component called leftover entities that have a component indicating that they're really likely going. They're really like going to the left. The component definition is very simple. A component with no data like this is called a tag component, and we'll put up with. Okay, so we'll create a new derive. Yep. Now we have to tell ECS to use the type with our register calls we add. Okay. It's easy peasy. Let's read. Okay. Yep. Yep. We'll copy that. Left mover. Yep. Now let's only make red smiley faces move left mover, so their definition grows to. Yep. Yes. We're gonna add a dot with here. Left mover. And I think that should be empty. Yep. Notice we've added one line with left mover. That's all it takes to add one more component to these entities. and not with the yellow at. Now actually make them move, we're going to define our first system. Systems are a way to contain entity component logic together, have them run independently. There's a lot of complex flexibility available, but we're going to keep it simple. Here's everything required with a left walker system. So struct left walker. This isn't a nice, as nice as simple as I'd like. Okay. Now to actually make them move, we're going to define our first system. Yep, we already talked about that. So we'll come over here and we'll actually struct left walker. IMPL. I don't know the syntax. This is a very weird syntax. System. Um, I think for now we got rendering working. I think tomorrow, or maybe I'll post 2 videos today, and I'll break this down into a separate video because we have rendering happening now, but now it's talking about getting movement working, and I would like to break that off into its own little video. So I think that's where we're calling it. I have to actually start work at this point as well. So thank you guys for watching. I'm gonna post another video today to get movement working. Thank you. Bye.